Hello and welcome back to the course of
Fundamental of Electronics and Electrical Engineering.
In this video lecture, I am going to continue with the unit 1, that is DC circuit. The topic that I am going to discuss in this video lecture is time domain analysis of first order RC circuit. Before I start the theory, let us understand each and every word of time domain analysis of first order RC circuit. When a circuit consists of energy storing element like capacitor and inductor, then analysis of such circuit involves the solution of differential equation. And if circuit contains only one energy storing element, then we are having first order differential equation if we analyze this kind of circuit. That's why the word used is a first order. Now, in this video lecture, I am going to discuss the first order RC circuit, the circuit which consists of series combination of resistor and capacitor across the DC source. Now, why it is known as time domain? If this analysis is done with respect to time t as a variable, then it is known as a time domain analysis. In the case of RC circuit, the analysis is variation of capacitor voltage with respect to time. So here you can see one circuit is there and one switch is there, and there are two positions of this switch. Initially assume that switch is not closed, it is in open condition. So circuit consists of two elements, resistor and capacitor. Both are connected in series. Now this series combination is connected across DC supply. So this circuit is analyzed under the DC condition. Now as initially switch is not closed, no current will flow, and there is no charge on the potential, there is no charge on the capacitor, and hence there is no potential difference across the capacitor. Now at time t is equal to 0, switch is closed, so current will start to flow, and as current is start to flow, there is a potential difference across the capacitor, so capacitor voltage will increase, but that will increase gradually. Now at t is equal to 0 is the initial condition. At t is equal to 0 time, exactly the Vc will be 0. After that, capacitor voltage will increase gradually. So suppose after t time, we are having Vc, that is a potential difference across the capacitor. I is a charging current and Q is a charge on the capacitor. Now as switch is connected to the position 1, now if we apply, now circuit is completed, current is already flowing. The value of the current will be decided by the value of the resistance. So charging time of the capacitor will be decided by the value of the R. Now if we apply KVL in this loop, we are getting total voltage V is equal to VR plus Vc, and VR is nothing but the IR. So we can write V is equal to IR plus Vc. Now we can write I is equal to dq by dt, because I is a charge divided by time and Q is nothing but the CV. But here capacitor voltage is denoted by Vc, so we can write Q is equal to CVc. So d by dt in bracket CVc, so is equal to C dVc by dt. If we put this value in this equation, we are getting V is equal to C dVc by dt into R plus Vc. So we can write V is equal to Vc plus Rc dVc by dt. Now we can write V minus Vc is equal to Rc dVc by dt. Now using the variable separable method, we can write dVc divided by V minus Vc is equal to 1 divided by Rc into dt. So in the left hand side we are having term the equation in the form of Vc, in the right hand side we are having equation in the form of time t. Now multiplying both the side by negative sign -1, so we can write minus dVc divided by V minus Vc is equal to -1 divided by Rc into dt. Now taking integration on both the sides, so integration minus dVc divided by V minus Vc is equal to integration -1 divided by Rc into dt. Left hand side integration is done with respect to Vc, right hand side integration is done with time variable t. If we take the integration of 1 divided by V minus Vc with respect to Vc, then we are getting the minus value. That's why in the above equation, both the sides are multiplied by negative sign. If we take the integration of 1 divided by V minus Vc with respect to Vc, we are getting log V minus Vc to the base e is equal to integration of 1 with respect to t is minus t. So minus t divided by Rc plus k. Now this is an equation which consists of constant, and k is a constant which is nothing but the constant of integration. So we have to first find out the value of the constant of integration using condition known as the initial condition. So at the initial level at the initial time, what was the value of the capacitor voltage? At time t is equal to 0 is the initial condition at which switch was closed. So at t is equal to 0, there is no charge on the capacitor, so Vc is 0. So at t is equal to 0, Vc was 0. Now putting this value in this equation, we are getting log V minus 0 is equal to 0 plus K. So we are getting K is equal to log V base E. Now, substituting the value of K in the equation 1, we are getting log V minus Vc to the base E is equal to minus T by Rc plus log V to the base E. Now, taking log V term to the left hand side, we can write log V minus Vc minus log V is equal to minus T by Rc. Now we know log X minus log Y is equal to log X divided by Y. So we can write log V minus Vc divided by Vc is equal to minus T by Rc. Now if you take anti-log on the both sides, we are getting V minus Vc divided by V is equal to E to the power minus T by Rc. So we can write V minus Vc is equal to V into E to the power minus T by Rc. And if we solve this equation, final capacitor voltage equation, the charging voltage equation, we are getting is nothing but the Vc is equal to V in bracket 1 minus E raised to minus T by Rc. Now we can define Rc, the product of resistance and capacitor, as a time constant, and that is denoted by lambda. So we can write Vc is equal to V in bracket 1 minus E to the power minus T divided by lambda. Now in this equation, suppose we put T is equal to lambda, then Vc we are getting is 0.632 V. V is the maximum value of the equation. So at time T is equal to lambda, we are getting Vc is equal to 0.63 V. That means what? Capacitor voltage reaches to 63.2% of its maximum value. And using this, we can define time constant as the time during which capacitor voltage rises to 0.632 times of its final steady value while charging process, or it reaches to 63.2% of its final value. Now this equation can be represented in terms of plot, in terms of graph. So it is a graph of capacitor voltage with respect to time t. That's why it is a time domain analysis. Now we are getting the exponential graph, and this is equation. This graph is of Vc is equal to V in bracket 1 minus E raised to minus T by Rc. Now this is a maximum value of the equation. Steady state value of this equation is V, that is a maximum value of the graph. Now at time t is equal to lambda, that is a time constant. After the value of time constant, what value are we are getting? 0.632 V. That means what? At time constant t, capacitor voltage reaches to 63.2% of its maximum value. Now let us derive the expression of charging current. So current is denoted by I is equal to C dVc by dt, where Vc we have already found. So putting that value of Vc, so I is equal to C, and taking the differentiation of Vc with respect to time. So we are getting I is equal to CV. V is a constant. Integration differentiation of 1 with respect to time is 0. Differentiation of this term will be minus E raised to minus T by Rc, and differentiation of this minus T by Rc will be minus 1 by Rc. So minus minus will be plus. So we can write I is equal to V by R E raised to minus T by Rc. So this is the expression for charging current. Now V by R is the maximum value of the charging current, and we can define V by R is equal to Im. So we can write I is equal to Im into E raised to minus T divided by Rc. Now in this equation, Rc is again time constant. So if we put T is equal to lambda or T is equal to Rc, then we are getting I is equal to 0.368 into Im, where Im is the maximum value of the charging current. So in this case, we can define time constant as a time taken by charging current of capacitor to drop to 0.368 times of its initial maximum value, because at time t is equal to 0, we are getting I is equal to Im, that is the maximum value. But after some time, that charging current will be reduced. Why charging current is reduced? Because capacitor voltage will reach to the voltage of battery, that is V. So as potential, there is same potential between the 2 points, current flowing will be start to decrease. So in this case, the time constant is defined as the time taken by charging current to drop to 0.368 times of its initial maximum value. Now this equation can be plotted in terms of graph. So this is the initial value where we are getting Im, that is V by R, at time t is equal to 0. Now after t is equal to lambda time, the capacitor current, charging current, decreases to 36.8% of its initial maximum value. Now let us understand discharging of capacitor. So here you can see in the charging process, switch was connected to position 1. Now suppose switch is thrown to position 2, then battery is not connected across series combination of resistor and capacitor. So capacitor will start to discharge its stored voltage. Now suppose Vc is a potential difference across the capacitor during discharging, and I is a discharging current, and Q is a charge on the capacitor. Now if we apply KVL in this loop, we can write 0 is equal to Vc plus IR. Now we know I is equal to dq by dt and Q is equal to CVC. So we can write I is equal to CdVc by dt. So our equation becomes 0 is equal to Vc plus RC dVc by dt. And dV, now using this variable separable method, we can write dVc divided by Vc is equal to minus dt divided by RC. Now taking integration both the side, taking the integration of left hand side with respect to Vc and right hand side with respect to time, we are getting log Vc to the base e is equal to integration of 1 with respect to time is t, so minus t divided by Rc plus K1, where K1 is a integration constant which can be found using initial condition. Now in this case, capacitor was initially fully charged. So this is an initial condition. Vc was approximately equal to V at time t is equal to 0, at time where t is equal to 0 when switch is connected to the position 2. So we can write at t is equal to 0, Vc is equal to V. And if we put this value in this equation, we are getting log V is equal to 0 plus K1. So now putting the value of K1, we can write K1 is equal to log V. Putting this value in the equation, we are getting log Vc is equal to minus t divided by Rc plus log V. Now taking log V to the left hand side, so we can write log Vc divided by V is equal to minus t divided by Rc. Now taking anti-log on both the sides, we are getting Vc divided by V is equal to e raised to minus t divided by Rc. So we can write Vc is equal to V into e raised to minus t divided by Rc, or we can write Vc is equal to V into e raised to minus t by lambda, where lambda is a time constant that we have already defined. Lambda is equal to Rc. Now variation of discharging current. So if we know that 0 is equal to Vc plus IR because no battery is connected, now we can write IR is equal to minus Vc. Now we know the equation of Vc, discharging voltage, that is V into e raised to minus t by lambda. So IR is equal to minus V into e raised to minus t by Rc. So I is equal to minus V divided by R into e raised to minus t by Rc, or e raised to minus t divided by lambda. Now V by R is the maximum value of this equation. So we can write I is equal to minus Im e raised to minus t divided by Rc. Now this is same equation of as we have found for charging capacitor charging current. Now only difference is what? Here negative sign is there because charging current and discharging current flows in the opposite direction. Now plotting this equation, we are getting the graph of Vc versus time, and maximum value of this equation is V. Now after time t is equal to lambda, if we put the t is equal to lambda in this equation, we are getting 0.368 of maximum value, that is V. So in this case, we can define time constant as the time taken by the capacitor voltage during discharging to drop 36.8% of its initial value. Now taking one example based on RC circuit. So what is the problem statement? It says that one capacitor of 0.1 microfarad is connected in series with 1000 ohm resistor, and this branch is connected across a 100 volt DC supply. We have to determine the time constant of the circuit, time taken by the capacitor to reach 63.2% of its final voltage. Final voltage is 100 or V, and third one, initial rate of charging. So taking first one, time constant. Now we know time constant is a product of resistor and capacitor, which is denoted by lambda. So lambda is equal to RC. that is, and value of capacitor is 0.1 into 10 raised to minus 6 into 1000. So we are getting 100 into 10 raised to minus 6 second. This is the time constant of the given circuit. Now next one, time taken by capacitor voltage to reach 63.2% of its value, maximum value. So we can write equation of capacitor voltage Vc is equal to V in bracket 1 minus e raised to minus t by lambda. So value of Vc is equal to, now capacitor voltage Vc reaches to 63.2% of its final voltage. So we can write 0.632 into V is equal to V in bracket 1 minus e to the power minus t divided by value of lambda, that is 100 into 10 raised to minus 6. So we can write e to the power minus t divided by 100 into 10 raised to minus 6 is equal to 0.368. If we solve this, we are getting t is equal to 100 milliseconds. So after 100 millisecond, capacitor voltage reached to 63.2% of its final voltage. So final voltage is 100 volts. So capacitor voltage will be 63.2 volt after 100 millisecond. Third one, initial rate of charging. Now initial condition will come into the picture in this case. Now we know V is equal to Vc plus Rc dVc by dt. Now at time t is equal to 0, Vc is 0. So we can write dVc by dt at t is equal to 0 is nothing but the initial rate of charging is equal to V divided by Rc. Now putting the value of V, R and C, that is dVc by dt at t is equal to 0 is equal to 100 divided by 100 into 10 raised to minus 6. So that is 1 into 10 raised to minus 6 volt per second. So this is the initial rate of charging. So to solve the example, you need to remember all the capacitor charging and discharging equation. So this is all about the today video lecture. In this video lecture, I have discussed about the time domain analysis of first order RC circuit, capacitor analysis of capacitor charging and discharging. Hope you have enjoyed the video. See you soon in the next video of the DC circuit. Thank you for watching.